Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on October 5th, 2025, about 3 days ago. The striking result is a non-autoregressive speech recognizer that matches state-of-the-art accuracy while decoding in parallel for a better accuracy-efficiency trade-off. The paper is titled Drax, Speech Recognition with Discrete Flow Matching. And as we'll see later, the implications for model training are quite significant. In short, this paper introduces an audio-conditioned middle distribution to align training with inference, supports controllable numbers of function evaluations, and backs the design with a generalization theory based on occupancy divergence. Also, the authors shared an official implementation on GitHub. You'll find a Python package with the transcriber API, ready to run examples for single and batch transcription, controls for sampling steps and temperature, a generate script, and clear install instructions with torch and torch audio dependencies, plus pointers to pre-trained models. On Hugging Face, Drax v1 offers downloadable 1.2 billion parameter multilingual ASR weights, plus Python examples for single file transcription, tuning sampling steps and temperature, and batch inference. Alright, Figure 1 shows how Drax closes the train versus inference gap by guiding decoding through realistic intermediate text. The left panel depicts a three-way probability path with an audio-conditioned middle distribution, which means a learned distribution proposes acoustically plausible partial transcripts. The center panel illustrates sampling steps that start from noise and progress toward the target through these hypotheses. The right panel outlines the architecture that pairs an audio encoder with a DiT-based decoder using cross-attention. Well, Figure 1 showed how training stays aligned with realistic hypotheses, and Figure 2 now quantifies the speed accuracy payoff. This figure demonstrates that Drax keeps runtime growth modest as sequences get longer, because decoding uses a fixed number of function evaluations. The left panel plots RTF times sequence against length, where lower curves mean faster decoding. The right panel compares word error rate to runtime percent, and the Drax variants trace a stronger Pareto frontier, giving clear control over speed versus accuracy. So while Figure 2 emphasized the speed accuracy curve, Table 1 shows how that plays out on English benchmarks. The table reports word error rate and real-time factor X, which is a runtime speed score where higher is faster. The bottom block highlights Drax rows. Plain Drax reaches a real-time factor near 32. With MBR scoring, the average word error rate drops to about 8.0. Whisper rescoring pushes the average word error rate to roughly 7.4. So, Table 2 compares multilingual recognition accuracy across several public datasets and shows that Drax is competitive with leading systems. It reports word error rate for alphabetic languages and character error rate for Chinese and Japanese, which means mistakes are counted per character rather than per word. Plain Drax holds strong in many entries, and MBR or whisper rescoring yields further drops. Overall, performance stays near the top from German through Chinese, while keeping the parallel decoding benefits. Alright, Figure 3 shows training curves under different probability paths and what that means for recognition accuracy. A probability path describes how the decoder moves from noise toward the correct transcript, and inserting an audio-conditioned middle means the model practices on realistic partial texts. The magenta curve stays lowest, which indicates fewer word errors across training. The gray curve lags because direct source-to-target paths miss those plausible intermediate states. So 2 takeaways stand out. The audio-conditioned middle distribution narrows the train-to-inference gap, which yields strong accuracy, and discrete flow matching gives controllable speed through a small number of function evaluations. The broader implication is that non-autoregressive speech recognition is ready for mainstream deployment. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.